Yeah, good afternoon, everyone. Let's start now. So we'll recall few topics. Graham Smith orthogonal. So first of all, am I audible and my screen is visible? Okay, thank you. So first of all, we'll revise Graham Smith or process of orthogonalization. So first we'll revise. Okay, so the in the case of Gram-Smith orthogonalization process, we'll convert n number of linearly independent vectors to n number of orthogonal vectors. Okay, so it's an algorithm. So we can convert. So suppose inputs are x1 to xn. So these are the linearly independent vectors. So then we can produce outputs as z1, z2, Zn, which are orthonormal vectors. Vectors. So the process is as follows. So first we will take y1 some other vector as x1. Okay. Then we'll find z1 equals to y1 divided by norm of y1. Okay. So the norm of z1 then becomes 1. So that's why this z1 can be a orthonormal vector. Then in the second step we'll uh, eliminate the okay, so we'll take y2 as x2 minus, so x2 is another linearly independent vector, so we'll eliminate some portion from x2. So which portion? So we'll eliminate some inner product of x2 and this z1. Okay, so this z1 is a unit norm vector, so we can find out the inner product between the vectors x2 and z1, and then we'll eliminate those that portion from x2. Then the remaining portion is y2 we are taking. Okay, and then then to make the uh, norm unit, so we'll divide this to y2 by norm of y2, and then in the so like that way we'll do. So then suppose there is a ith stage. So in the ith stage we will find yi as equals to xi minus inner product of xi and z1 minus xi and z2 dot inner product of xi and okay, and then zi equals to yi divided by norm of yi. So that can be written as xi minus summation of. So this is the process. So we'll take an example. let's x1 be let us take these three vectors. So we'll convert these three linearly independent vectors. So you can check that this x1, x2, and uh, x3 are linearly independent vectors. So we'll convert these three linearly independent vectors to three orthonormal vectors. So in the first step, we'll take y1 equals to x1. That means this is same as 1, 1, 1. Then what is the norm of x1? That is equals to 1 plus 1. So the first orthonormal vector is this is the first orthonormal vector. Then in the second step, we'll find out the portion of x2 on z1. Okay, that means x2 transpose z1. That is, so x2 is, what is x2? x2 is 0 to 1, 1. So this is the 0 to 1, 1. So y2 equals to x2 minus inner product of x2 and z1. That is, x2 is 0 to 1, 1. Minus. Hello? Are you asking something? So z1 was 1 by root 3, 1 by root 3, 1 by root 3, 0. Now we'll find out the norm of y2, that is equals to root over minus 1 square, 1 square. So in the third step, we should find out the okay. So we'll find out the all the portion. So that means x3 comma z1, that is equals to x3 transpose z1. What was the x3? X3 was minus 1, 1, 3, minus 3, 1 by root 3, 1 by root 3, 1 by root 3, 0. So that is minus 1 by root 3 plus 1 by root 3 minus 3 by root 3. Then we'll find out x3 and z2 inner product. It is x3 transpose z2. Okay, so this inner product of x3 and z2 is root 3. And this I have written this as x3 transpose z2. So that is the same as z2 transpose x3 actually. Because all are real numbers here. That's why. So now we'll find out what is y3. Y3 is x3 minus, so that is, so x3 is minus 1, 1, minus 3 and 1. Then x3 and z1 is minus root 3. So this is the z2, and then yeah, it is minus 1, 1, minus 3, 1. Okay, so this is the y3. Then we'll find out the norm of y3. Two 4 root 6. So z3 equals to y3 divided by norm of y3 is equals to, so these are the z1 z2. So this z3 z2 and this z1. So these are the three orthonormal vectors we get. Okay. So one more interesting point is that, so we can write down A, which has linearly independent columns, like here it is there x1, x1, x2, and x3, that can be written as orthonormal. Okay, and so orthonormal. So these z1, z2, and z3 are the orthonormal vectors. And what will be this matrix? This matrix is a upper triangular matrix. So it can be written as like this. Okay, so here, so it's a upper triangular matrix. So it is it can be written as Q. It can be written as R. So what will be the exact value for this case? Okay, so this will be, A will be, so what is the z1? Z1 is 1 by root 3, 1 by root 3, 1 by root 3, 0. And z2 is minus 1 by root 3, then 1 by root 3, 0, 1 by root 3. And z3 here is 1 by root 6, 1 by root 6, minus 2 by root 6, and 0. So this is a 4 plus 3 matrix. So this is a R matrix 3 cross 3. So what it should be? So first vector is y1. Okay, so sorry, x1. So x1 is equals to, so in this equation, x1 equals to y1, which is so this is the, so x1 equals to root 3 z1. So here we can write down x1. So first vector is x1. So this is the root 3 into z1, and others are zeros. Okay, and then the second one is so in the second step, so second vector is x2. X2 is y2 So here, okay, so here we can write down Z2 equals to, so 1 by norm of Y2. So what is Y2? X2 minus this. X2 minus what is this thing? This is the root 3. Root 3 and Z1. That can be written as X2 equals to, so norm of Y2 is root 3. So root 3 Z2 into, sorry, hmm. So X2 equals to root 3 Z2 plus root 3 Z1. So then X2 is the second vector. So this is the X1, X2, this is X3. So then, so X2 is the root 3 Z1 plus root 3 Z2. So this is the Z1, Z2, Z3. So root 3 Z1, then root 3 Z2. Okay. And then Z3 is, okay. So what is the X3? So here we find out the Z3 equals to 1 by, so root 6 is into Y3. Y3 is equals to this X3 minus 3 minus. So X2, X3 and Z1 inner product. X3 and Z1 inner product is minus root 3. Then X3 and Z2. X3 and Z2 is root 3. So from this equation, so that can be written as X3 equals to root 6 Z3 minus root 3 Z1 plus root 3 Z2. So it is my root 6, so my, that means minus root 3 Z1. So minus root 3 Z1, then plus root 3 Z2 and root 6 this. So this is the R matrix, upper triangular. So this decomposition is called Q or decomposition. Okay, so then I will start. What is the second topic is what is similar matrix? Matrix B, it's a M, n cross M matrix. So a matrix B is said to be similar to another matrix A. So if there exist non-singular. Non-singular means inverse should exist. That means invertible. So non-singular matrix is such that so so a matrix B is said to be similar to another matrix A if there exists a non-singular matrix A such that B can be written as B equals to S inverse AS. Okay, where S is the non-singular matrix. Then we can say B is similar to A. So let's say square matrix A. So that is said to be diagonalizable if it is similar to a diagonal matrix. So that is A. We can write down A as so this is a diagonal matrix. So we have one theorem. We will not prove the theorem. It is just a theorem that is so A is a matrix. So A is diagonalizable if and only if A has so n linearly independent eigenvectors. That is A is non-defective. So it's a theorem. We will prove this theorem. Then third topic is what is unitary matrix. So U is a matrix which is unitary if we can write down U Hermitian U is equals to U Hermitian equals to an identity matrix. Okay. So we have the following theorems. First one is U Hermitian equals to U inverse. So it's very clear, obvious from this equation. So U Hermitian equals to U inverse. And second one is norm of Ux equals to norm of X. So the proof is very simple. So Ux norm square can be written as Ux Hermitian Ux. that is equals to that is equal to x Hermitian u Hermitian ux. Then u Hermitian u is I. So x Hermitian I x. I is the identity matrix. So x Hermitian x is same as norm of x square. Okay, same. Now the next topic is what is normal matrix. Is normal if A Hermitian A equals to A Hermitian. So obviously the examples, so unitary matrix will also be a normal matrix. Another one is one kind of matrix is Hermitian matrix, where this A Hermitian becomes A. So then A square equals to A square. Hermitian matrix, then symmetric matrix. Okay. So another theorem is if A is a normal matrix, A is unitarily diagonalizable. So that means so A can be written as some unitary matrix inverse a diagonal matrix and then U. Okay, so we know that U inverse equals to U Hermitian also. So then U Hermitian sigma U. So it's a diagonal. And um, so sorry, one more thing. Equals to sigma is a diagonal matrix. As A is similar to a diagonal matrix, then we can write down U Hermitian A U equals to sigma. As U is a unitary matrix, so we can write down U inverse equals to U Hermitian. So then A is equals to, so put this multiply with U in the left side. So it will be U sigma, then U Hermitian in the right side. So we can write down A like this for okay, and then where columns of U must be a complete orthonormal set of eigenvectors for A, and the diagonal entries are associated eigenvalues. Okay, so then one more topic is the matrix inversion lemma. So it's already mentioned in the main class. It is U A plus U C V inverse equals to A inverse minus A inverse U C inverse plus B A inverse U inverse B A inverse. So conditions are number one, A inverse should exist. Number two, C inverse should also exist. Number three, C inverse plus B A U is also should exist. Okay, so the proof of this matrix inversion lemma is very simple. So if you multiply with A plus UCV with the right hand portion like this portion, so if you then you will find out that this becomes an identity matrix. Okay, so one example. So one example. So put C equals to 1. C is a matrix, but let's take a scalar C equals to 1, and U is a matrix. So U is a some n cross 1 vector. It's a vector, and V also has a another vector, that is V transpose. Okay, so this becomes 1 cross n vector. Okay, now let's now put an A equals to identity n cross n. Okay, so then put this whole things A, C, U, V in this equation, then you will find out that I plus U V transpose inverse equals to. So now put this equation. So A inverse, that means I inverse is I. So I minus I into U. So U is a U. Then C inverse is 1. So then 1 plus and V A inverse U. So V is V transpose and A inverse is I. Then it's a U is inverse, and then V transpose and A inverse is I. Okay. So this becomes, so this is a scalar. So this becomes I minus U B transpose divided by 1 plus B transpose U. So the condition here, the condition for the existence of inverse is 1 plus B transpose U should not be 0. If it is 0, then it is infinite. So inverse can't exist then. Okay, so then the next topic is complex convex function. Convex function. So a function fx is called convex function if for every x comma y in r power n, for every theta belongs to 0 comma 1, we have f of theta x plus 1 minus theta y is less than equal to theta f of x plus 1 minus theta f of y. Okay, so let's take an example. So let's take x and y as our scalars. So then the example becomes, so let's take this is a f of, sorry, of t. Okay, so this is a function f of t, and this is the x, this is y. So theta is theta belongs to 0 comma 1. That means theta, so 0 less than equals to theta less than equals to 1. So this means, so theta will fall in the interval 0 to 1. And so then that means that this theta x plus 1 minus theta y will fall in this domain, actually in this region, theta x plus 1 minus theta y. Okay, so in this region if you see, okay, in this region if you see, so theta fx plus 1 minus theta fy, so this is a straight line, this line, so this is theta fx plus 1 minus theta fy, so this is a straight line and this is the function value. Okay, okay, so you see that it's very obvious that this function is below the straight line, so the value of that function is less than equals to this theta fx plus 1 minus theta fy. So hence this function is a convex function. And one more thing is that so if f of theta is convex, if dash, so if f of t is convex, then f dash t is a monotonically increasing function. Function. So that means f double dash t is greater than equals to 0. Okay, so if double dash t is greater than or equal to 0, then we can say that ft is a convex function. Okay, so then the second topic is convex set. So let omega be a set, then so a set omega is called convex set if for every x and y belongs to omega, we have tx plus 1 minus ty belongs to omega for all t belongs to 0, 1. This is the convex set. And next topic is what is convex optimization problem. And the example of a convex set already professor has given. So so this is a convex set. If you add these two line, all will fall in this set. Okay, any two lines. Okay, so optimal convex optimization problem. A problem of minimizing a convex function within a convex set is called convex optimization problem. Okay, so now we'll start some sample problems. Okay, before that, one more topic is affine set. So already professor has told, but still, what is affine set? So a set, so everything is same. Omega is called a convex set. So for this case, a set omega tilde is called affine set. Affine set. If for all x and y belongs to omega tilde, we have Ex plus 1 minus ty belongs to omega tilde for all t belongs to a real number. Belongs to real numbers. Okay, so this is the affine set formula. So it's obvious that convex set will also be a affine set because 0 to 1 that also belongs to a real number. So belongs to real number. So then next topic is so some sample problems we'll solve now. The rank of a matrix is equal to number one option is minimum number of linearly independent columns, B maximum number of linearly dependent columns, number C is maximum number of linearly independent columns, and number D is minimum number of linearly dependent columns. Okay, so it's obvious that it's a maximum number of linearly independent columns. So the option C. And the second question is, so let's take a matrix A equals to 1, 2, 3, 3, 2, 4, 6, 9, 2, 6, 7, 6. So the question is find row reduced echelon form. What is the RREF form of A? So this is the okay. So now how to find out? So we should do some elementary row operations. So solution is what should we do? So A, this is a matrix. So we'll do uh, so we'll subtract the some portion of row one from row two. So it's twice of row one. So that will give this matrix as okay. So this matrix has one first row is same, then 0, 4, 0, 0, 3, then R3 minus 2 or 1, 0. Okay, so then we'll do uh, okay. So 2 R1 is 2, 2, 2, 2, 0, 2, 4, 0, 2, 6, 0, then 3, and then 0, 2, 2, 4, 2, 2, 2, 4. So 1, 0. Okay, fine. So it will be if I interchange between row, so row 2 and then row 3. So row 3 interchange will give 1, 2, 3, 3, 0, 2, 1, 0, and 0, 0, 0, 3. Okay, so the rank is so number of pivots. So this is a 1, 2, and 3. rank is, sorry, not rank. So this is the row reduced echelon form. Okay, so rank of A is equals to 3. Okay, so is it correct? 1, 2, hmm, 3. Okay, so then the next question is second question. Okay, so third question is the multivariate distribution for n IID Gaussian random variables x1 with mean 0 and variance 1 is given as, okay, so n IID random variables. So suppose, so first f of xi, okay, what will be the distribution of any one random variable is equals to root over 2 pi sigma square. Sigma is 1, so 2 pi e power minus x I minus 0, so it's a 0 square. Okay, so divided by 2 into 1, 2 sigma square, so it's a 2 only. So then what will be the distribution of f of x1 xn all will be multiplication of 1 to n f of xi that is equal to, as their IID, so this is the solution. Is as same as, so this is the norm, so summation, so it's the norm x square by 2, okay, where x equals to x1 x2 xn. So then the fourth question is So find the basis for each of the four fundamental subspaces. So find the basis for each of the four fundamental subspaces associated with the matrix A equals to. So the matrix is 1, 3, 2, 2, 6, 4, and 0, 1, 1, 1, 9, 7, 1, 6, 5. Okay. So we need to find out the uh, basis for each subspaces. That is the range space of A, and then that means null space of A, null space of A transpose, and range space of A transpose of all four. Okay, so first let's find out the rank. So it's a 1, 2, 3, 3 cross 1, 2, 3, 4, 5, 5, 3 cross 4, 3 cross 5 matrix. Okay, so then we can write down rank of A is less than equal to minimum of 3 comma 5. Okay, that is equals to 3. So that means rank of A is less than equals to 3. But what is the rank? We need to find out. So you can see that R2, so it's 3. Okay, so if you see that R2 equals to R1 plus R3. Okay, you can check that. 1 second. Till 7 2. Okay. 1 2. So it will be 2. So 7 2 1 6 3 and 6. Okay. So that is satisfied. So that gives the R1 and R2 are linearly independent rows. So that means number of linearly independent rows goes to 2. So that means uh, dimension of row space, that means range space of A transpose equals to 2. That is the rank. Rank is 2. So, so rank is equals to 2. Okay. So ultimately what is the case? So suppose this is the orthogonal decomposition of the four fundamental subspaces. So this is the, so number of rows are three rows. So or three is the or five. Okay, so each column has three elements. So here somewhere this is the range space of A. This is the null space of A transpose. Okay, and here the dimension is 2. So here the dimension is equals to 1. So only two bases will be there for the range space and only one basis will be there for the null space of A transpose. And here it's a range space of A transpose. Dimension is 2 and its null space of A dimension is 3. So there are two bases for row space of A and three bases for the null space of A. Okay, now what should be those bases? We need to find out. So now, so basis means the linearly independent vectors of that space. That means the maximum number of linearly independent vectors in the range space of A. So that we should find out. So this, suppose this is the basis B of range space of A. So this is the maximum number of maximum linearly independent vectors. So mm, okay, so here if you see that is row 1 and row 2. So these two are linearly independent uh, vectors. Okay, so sorry. And here for the column, so this is the 1 3 2. So 132 and then 0 1 1. So this and this you can check, these are the linear independent columns also, all are dependent, everything. Else this I mean remaining all the columns are dependent. So the 132 and 0 1 1, these two are the basis for the range space of A, and what will be the basis for the range space of A transpose. So it's a set of rows only. So okay, so two, but what should be those things? So this 12021. So this is the 12021 first row, and then third row 24175. Okay. And now basis for the null space of A. How to find out? Okay. So to find out, so null space of A means so
So
X.
please repeat it. So can you please repeat it?
Repeat for which? Okay, so let's repeat again. So first, let's take a matrix A, which is a 3 cross 5 matrix. So we need to find out the basis for each fundamental subspace of that matrix. Okay, so first of all, we need to find out the rank. So here the rank is less than equals to 3 comma 5. That means rank is less than equals to 3. Then if you see that there are three rows, but out of those three rows, the second row is the addition of first and third row. So that means R1 and R2 are the linearly independent rows, but R3, sorry, R1 and 1 minute, sorry, this will be, so R1 and R3 are the linearly independent rows, and R2 is the dependent row. So number of linearly independent rows is 2 actually. So we can say that dimension of range space of A transpose, that means this portion. So this portion dimension is 2. And range space, so we know that this dimension of this range space of A transpose and range space of A is same actually. That means rank of A and rank of A transpose is same. So that means if it has dimension of 2, then it will have dimension of 2. Okay. Then so rank of A is equals to 2 now. Then so this is the orthogonal decomposition of the subspaces. I uh, taught this thing last day. So here, so this range space of A is orthogonal to null space of A transpose. So if range space of A has number of bases two bases, then null space of A transpose will have only one basis, because this whole space will belongs to R cube. That means so see, each column has three elements. So that means each column, I mean the column space will be in the R cube domain. So this is the R cube. Okay. So okay, so then, but the dimension is 2 for the range space of A. So the dimension of null space of A transpose will be 1, because if you see that only 3 bases should be there for R cube, but 2 will be there in the range space. So 1 will be there only for the null space of A transpose. Similarly, for the rows, if each and every row has 5 elements. Okay, so the range space of A transpose or row space of A will be in the R power 5 domain. Okay, but out of the 5 bases, only 2 will be there for the range space of A transpose. So for the null space of A, there will be 5 minus 2, 3 bases. Okay. Now we are finding out the basis of each subspaces. So let's find out the basis of range space of A. Okay. So for the range space of A, number of bases is 2. So range space of A means the number of linearly independent columns. Okay. So here there are 1, 2, 3, 4, 5. 5 columns are there. Out of these 5 columns, 2 will be linearly independent. So so if you see that first and third column, they are linearly independent. You can find out other 2 columns also linearly independent, but let's take 2 out of these 5. Any 2 will be linearly independent. Okay. I mean, yeah. So here 132 and 011, they are linearly independent. So if you if you find out one column, you can't find out one column as a scalar multiple of other column actually. So that's why column 1 and third column is are linearly independent columns. So those linearly independent columns we can take as basis also. So for the basis of range space of A, we can write down 1 3 2 and 0 1 1. Okay. Now, similarly, we can find out the basis for range space of A transpose. So that means the number of the linearly independent rows actually. So here we have already shown that R1 and R3 are the linearly independent rows. So 1 2 0 2 1 and 2 4 1 7 5. Those two are linearly independent rows. So that's why these are the basis for the range space of A transpose. Okay. Okay. So now we are going to find out. So is it clear up to this for you?
Yes, sir. Yes.
Okay, so now we'll find out the basis for null space of A. Okay, so null space of A will contain those x vectors such that Ax is 0. So, okay, so now how to show? Okay, so Ax equals to 0. That means A is this matrix. So 1, 3, 1, 2, 0, 2, 1, 1, 2, 0, 2, 1, then 3, 6, 1, 9, 6, 2, 4, 1, 7, 5. Okay. Now we'll find out the LUD, sorry, Gauss elimination. So using Gauss elimination, okay, we'll find out the what is X. So let's find out the row that. So let's do some row operations. So it can be this can be done as so R2 3 R1 R3 minus 2 R1. This will give 1 2 0 2 1. So 0 0 1 3 0 0 1. Then we'll do so here there is only two pivots, so rank is 2. So this is the eliminated form. So this into x1, x2, and x3. Sorry. So x1, x2, x3, x4, and x5. So is equals to 0. So if you see that there are only two efficient or unique columns. So two unique equations, equations and five unknowns. So how to solve two? So how to find out five unknowns from two equations? So you will find out only two unknowns from this equation. So it's clear that there will be only two. Uh,
So
Sorry,
we
there.
are as free. We set other variables as free, as sir told.
Can you repeat?
We set other variables as free, like three variables as free, and then we take two and then solve it.
Yeah, yeah, correct only. Yeah, yeah. That's why actually. So we can solve that like that way. So yeah. So by that way only we will get three unique. basis. So yeah, let's solve this. The first equation is x1 plus 2x2 plus 2x4 plus x5, and second one is x3 plus x4. Okay, so we'll do these things. So let's take x2 equals to some 1, x4 equals to 0, and x5 equals to 0. Okay, so this will give x3 equals to 0 from 2, and then x2 equals to 1, x4 equals to 0. So this is 1 0 0. So then this will give x1 equals to 2x2, so minus 2. Now let's put x2 equals to 0 and x4 equals to 1, x5 equals to 0. So this will give mm, okay, so x3 equals to x4 and x5, so minus x4 minus 3, x3 equals to minus 3, and then x2 equals to 0 and x4 equals to 1, so x4 equals to 1, so 2x, so x1 equals to minus 2 from 1. Then let's take x2 equals to 0 and x4 equals to 0, and then x5 equals to 1. So this will give x3 equals to x1 x5, so minus 3, x3 equals to minus 3, and then x2 x4 0, so x2 x4 0, x5, that means minus 1. So the linear independent bases are 1 comma okay 3. So which are those? One is this thing, so this one and this one. That means in the first case x1 equals to minus 2, so minus 2, then x2 equals to 1 0 4 0. Oh, so here this is the x1, x1 x2, so minus 2 1, minus 2 1, then x3, x3 is 0, then x4, x4 is 0, x5 is also 0. Okay, so in the second case, x1 equals to 1. Sorry, x1 equals to 1, x2 equals to 0. X1 equals to minus 2, 0. X1 equals to minus 2, x2 equals to 0, and then x3 equals to minus 3, and x4 equals to 1, x5 equals to 0. And then in the third case, x1 equals to minus 1, x2 equals to 0, x3 equals to minus 3, x4 equals to 0, x5 equals to 1. So these three are the bases. So similarly, find basis for null space of A transpose from the equation A transpose X equals to 0. Okay, so this will have only one basis. So okay, and one more thing is that you can check that see null space of A and range space of A transpose are orthogonal. So let's take range space of A transpose. So let's take this 1 2 0 2 1 is a vector from range space of A transpose, and another one vector from null space of A transpose. Null space of A equals to minus 2 1 0 0. So if we multiply this minus 2 1 0 0 transpose this 1 2 0 2 1, so this will give uh, 0, okay, as they are orthogonal. Okay, so then one more. Next question is number of question 4. So then is a 5 or fifth question. The fifth question is what is the trace of AX Hermitian equals to what if lambda comma x eigenvalue and eigenvector pair for A. So the solution is the trace of so AX Hermitian. So trace of x. So we can write down A and AX equals to so as lambda and x eigenvalues and eigenvectors of A. So AX equals to lambda x. We can write down. So here AX equals to lambda x. We can write down. So lambda x and x Hermitian. That is trace of lambda in lambda into trace of x Hermitian. Okay. So this is equals to lambda into trace of sorry. You can check that trace of x Hermitian equals to lambda into x Hermitian x is equals to lambda norm of x square. Okay, so this is the solution. And then the next question is consider the minimization problem of so let's take fx equals to ax minus tau ln x. So we need to show that is it a convex function or not. So solution is as follows. So we show that we need to check f double dash x. So if it is 0, then greater than equals to 0, then it's a convex function. So let's check that. So f of x equals to a plus minus tau log x. So f dash x equals to minus tau by x. Double dash x equals to tau by x square then minus 1. Okay. So okay, fine. So if double dash x is greater than equal to 0, if tau greater than equals to 0. Okay. So for that case, fx is convex function. So the next question is the constraint set convex set? So we need to show that is this set convex or not. Okay. So let W be a set set. Wait. Uh, okay, let's take this constant set as W. W is the this constant set and x1 comma x2 belongs to W. Okay. So that means 0 less than equals to x1 less x2 equals to 1. So one equation, and second one is x1 plus x2. Oh, sorry. So let's take x as a vector. So it's x1 and x2 two elements are there. So and y as also a vector that is equals to y1 and y2. Those two vectors belong to omega. So then 0 less than equals to x1, x2 less than equals to 1, and 0 less than equals to y1, y2 less than equals to 1, and x1 plus x2 equals to 1, and y1 plus y2 equals to 1. Okay, so now we need to show that tx plus 1 minus ty belongs to omega or not, where t falls from 0 to 1. Okay, so how to check? So let's check. Hmm. So okay. So let z is another vector tx plus 1 minus ty, that is t x1 tx2 plus 1 minus ty y1 1 minus ty y2, that is equals to tx1 plus 1 minus tx2, sorry, y1, then tx2 plus 1 minus ty y2. Okay, so obvious that so here x1 and x2 belongs to 0 to 1. So 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 0, x1 and x2 is 1. So that means mm, it will be tx1 plus 1 minus tx2 will also from 0 to 1, and 0 y1 and y2. Okay, so that means 0 ty1 plus 1 minus ty2, that also. Okay, so we can write down that 0. So this z1 and z2 will be from 0 to 1. Okay, so one more condition we need to show, that is z1 plus z2 equals to 1. How to show? So how to show? So need to show z1 plus z2 equals to 1. So now z1 equals to, or is z1 equals to tx1 plus 1 minus ty1. So tx1 plus 1 minus ty1. Okay, and z2 equals to tx2 plus 1 minus ty2. So z1 plus z2 equals to tx1 plus x2 plus 1 minus ty1 plus y2. Okay, so y1 plus y2 equals to 1. So this is 1, this is also 1. So that is equals to t plus 1 minus t equals to 1. So, z1 comma z2 will be from 0 to 1, and z1 plus z2 equals to 1. So z belongs to omega. Hence, this omega is a convex set. Okay. So one more question, one last question. That is eighth question. Question number 8. Find the determinant of I plus CD transpose. What it should be? Okay, determinant of I plus CD transpose will be what? So solution. So let's take a matrix A, B, C, and D. This A, B, C, and D are the block matrices for a whole matrix. This okay. So and A. So okay. So, so this okay. So we can write down determinant of this matrix, block diagonal matrix. So this is the one formula is there. So okay, that is equals to, the formula is date A into date D minus C A inverse B, if A inverse exists, and that is also same as date of D, date of A minus B D inverse C if D inverse exists. So there are two formulas. So if A inverse exists, then we can write down this determinant of this equals to determinant of A multiplied with determinant of D minus C A inverse B. And if D inverse exists, that means if D is invertible, then that determinant is equals to determinant of D multiplied with determinant of A minus B D inverse C. So this proof of these two formulas I will not show. So you can check in one book, Carl Mayer, there you can check. So these are the two formulas. So we will use this formula to find the determinant of I plus CD transpose. So it is very helpful. So let we need to find. So let us find determinant of I C minus D transpose and 1. Okay, determinant of this. Okay, so I is the n cross n matrix, C is the n cross 1 vector, D transpose is 1 cross n, and is the 1 is a scalar. So if you check, this is the n cross 1 into n cross 1. So n cross 1 in times n cross 1 matrix it is. So that is, so we'll use these two formulas. Okay, so 1 and 2. Okay, so first date of A means determinant of this identity matrix. So this is the 1. So determinant of I, then determinant of D minus. So D is 1 here. So 1 minus C A inverse. C is this. I mean that is D transpose, and A inverse B, that is I inverse, and B is this C. Okay, so this from 1. That is the determinant of I equals to 1. This is the determinant of 1 plus D transpose C. Okay, so this is the scalar. This is 1 plus D transpose C. And we can write down using equation 2, that is determinant of D, that is 1. So 1 into determinant of A means I, so I minus B D inverse. B means C. So C D inverse is minus D transpose. Okay, so that is equals to determinant of I plus C D transpose from 2. So these two are same. because they are the determinants of same matrix. So we can write down determinant of I plus C D transpose same as 1 plus D transpose C. Okay. So one thing here in the first in at the beginning I saw that so I show that this I plus UV transpose, inverse of this I plus UV transpose is equals to I minus UV transpose by 1 plus V transpose U. So this was the determinant. So this denominator is the determinant term. Okay. So that's why actually. So it's yeah. So that's what I need to show here. So okay. Thank you. That's all for the today. For today, and have a rest weekend. Have a happy weekend. If you have any question, you can ask me. One more thing is I have uploaded the last day's video and the notes in one Google Drive. So did you guys get that link or I should send?
Send it, sir.
Okay, I will send then. Okay. Okay, guys. Thank you for joining. So yeah, are you asking anything?
No, sir. No, sir.
Okay. Thank you.